Okay, so now we're going to talk about the determinant and the cross product. Now, the dot product produces a scalar. It just produces a number. The cross product actually produces a vector. Okay, now, these things, how do we think about the difference between them? Okay, now, we saw in the last class that the dot product will describe a plane because the vector that is perpendicular to the plane actually describes the plane. Because if you do the dot product with the normal vector with any vector that lies within that plane, you're going to get 0. So that's a way to describe a plane in space. Okay? You have to have a point that exists within this plane, and then you need to know the normal vector to that plane. But what if you're just given points within the plane, and you're not given this normal vector? How would you go about finding them? Well, let's say we have that. So let's say we're just given 3 points that exist within a plane. Okay, now these 3 points, we have a point that's in the middle, and then we have 2 other points within the plane that'll give us 2 vectors within the plane. And we say, okay, great. How do I actually describe this plane? How do I figure out what the normal vector is to this plane? Okay. Well, if you do now A cross B, that will actually give you N. Okay? That'll give you the vector that is going to be perpendicular to that plane. Okay? So A dot B, N dot A or B is going to equal 0, because that vector is going to be perpendicular to the plane. Okay? But if I've just got the 2 vectors and I want to figure out, well, what is the normal vector of the plane? The vector that is perpendicular to that plane. Okay? Well, we're going to have to do the cross product. Okay? In case some of y'all don't remember, what is the cross product? It is going to be a determinant. So let's go ahead and let's review how to take a determinant, because that is a cross product. So, if I was going to set this up, let's set up a matrix, and we'd take the determinant of the 3 by, well, all right, let's do a smaller one first. Say A, B, C, D. Treat it like that, and that would be A, B, minus B, C. Okay, so that's the determinant of a 2 by 2 matrix. But we're not going to do a cross product on a 2 by 2 matrix. We're going to have to do a 3 by 3 matrix. Okay? So the determinant of a 3 by 3 matrix is say A, B, C, D, E, F, G, H, I. And I should have brought some color markers to do this. Okay, so what's going to happen? This is going to go plus, minus, plus. Okay? So what I'm going to do is I'm going to take this point right here, A, and I'm going to take the determinant of everything that's not going to be associated with it. Okay, so for this one. So that would equal A times E I minus F H. Okay? and then I'm going to subtract b. Okay? Now, whenever I'm looking at b, I'm going to be looking at this one and this one. Okay? So everything that is not in the going column of b. Okay? So this would be b times I minus f times g. Okay? And now plus c. Now, when I'm dealing with c, I'm just going to be looking at these guys over here. Okay? So that's going to be e h minus e g. Okay. So that's going to be the determinant of the matrix, the 3 by 3 matrix. Okay. So if we're going to do the cross product, I guess I'll come as positive. Okay. So if A is going to equal the vector A1, A2, A3, and B is going to equal B1, B2, B3. Okay. A cross B is going to equal the determinant of I, J, K, A1, B2, A3, B1, B2, B3. Okay. And just like in the last video, I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. This is basically, this is a vector in the x direction, a vector in the y direction, a vector in the z direction. Okay? And so, if I'm going to take the determinant of this guy right here, this is going to equal I, and multiplied by A2, B3 minus A3, B2, and minus J, A1, B3 minus A3, B1, and then plus K times A1, B2 minus A2, B1. So this is the cross product. Okay, and there's another interesting fact that ends up happening with the cross product. The magnitude of A cross B actually equals the magnitude of A times the magnitude of B, now multiplied by sine of A. Okay? And remember from the previous problem that A dot B equals the magnitude of A times the magnitude of B multiplied by cosine of A. So this is the difference between the dot product and the cross product. All right, so what do we actually get from this? So if A plus B equals 0, So in the normal Euclidean sense, the dot product and the cross product, the difference between them is they're describing something that is parallel or perpendicular whether or not they equal zero. Okay? And think about it, one is sine of theta. So what is sine of zero? Sine of zero is zero. That means the vectors will be parallel to each other. And what is cosine of pi over 2? Cosine of pi over 2 is zero. That means they'd be perpendicular to each other. So this is a way of actually, once again, in a normal Euclidean sense, of describing something that would be parallel or perpendicular. And also think about it this way, whenever we're talking about whether two vectors would be parallel, if I'm describing, we started out like this, describing the turbident and the cross product. So you have the right-hand rule that says whenever you do the cross product, the vector ends up poking up where your thumb is as you curl your hand. But if you got two vectors that are parallel to each other, they do not form a plane. What do? They form a line. And so you cannot create a plane from that line. So that's the major difference between the dot product and the cross product. Is one is parallel and one is perpendicular. Now, this definition right here of parallel and perpendicular does end up coming into some contradictions. I mean, not contradictions, but can we ask ourselves, is there any vector that is both parallel and perpendicular to every other vector in the world? Let me think about it. Well, according to this definition right here, the zero vector, if you just put 0, 0, 0 as a vector, if you dot product that with anybody, it's going to equal 0. Okay, so it's perpendicular to everybody. If you do a cross product, think about if you were doing a cross product with a determinant right here, you would have, let's say A1, A2, A3 is 0, 0, 0, 0, 0, 0, 0, all of them are 0. So it's parallel as well. So the zero vector, according to this definition, defined by the dot product and cross product, is both parallel and perpendicular to every other vector in the world. So that's the cross product.